Hi everybody and welcome. Today's videos we're going to be focusing on practicing with some of the calculations behind these. The first few videos of this unit we really kind of focused on the concepts and understanding the context of things. And today we're really going to kind of take a step back from the word problems and jump into just some of the basic calculations. So the videos won't be super in-depth or long today. Most of your time is going to be honestly spent doing some practice questions. So big goal of these videos, get the basic definitions down, just recap them from previous classes. And then the last thing that we'll do here together is go through some practice problems. So some extra practice problems, some extra examples, and using that, we're hopefully going to be put in a good position to be successful applying these skills in the many different ways that we're going to see them on future assessments. So with that being said, our first definition is when we have events that are not mutually exclusive. And what this means is both can happen at the same time. So an example of this would be, I guess if you're looking at candy bars and you're like, oh, I want a chocolate candy bar, but it would also be nice to have a candy bar with some peanuts. Well, it is possible to have a chocolate bar that has peanuts in it. So because both of those things can come together at the same time, it's not just a chocolate bar or just a bar of peanuts. You can have a chocolate peanut bar. So that would be an example of not mutually exclusive. Again, you can have both together. So in this case, the probability of A or B, so either of them happening, is the probability of A plus the probability of B minus the probability of both A and B happening at the same time. So that's definition number one. When we have events that are mutually exclusive, this means the first doesn't affect the second. They are completely independent and separate events. In that case, they don't affect each other. There is no probability of them happening together because it's simply impossible. It's basically the same formula, just missing that last piece. So again, because they're unrelated, this piece of the formula is 0. It's impossible for them to happen together. So as a result, we have a different formula. So we're going to go through some practice problems now, but these are the key definitions for our mutually exclusive and non-mutually exclusive or independent and dependent events here. So we can start off with some examples from decks of cards, and we'll actually focus on most of those for here because those are some pretty good applications, and we can also do one with rolling some die. So I know a few of us in class have said, Mr. Harv, why do you like cards so much? Well, it's a good example of probability. So I'll give that a rest for a second. We'll do that as our second example. Our first one, though, let's talk about rolling some die. So you roll a 6-sided die, and you roll a 2. You roll a 6-sided die, and you get an even number. So let's just quickly recap with a 6-sided die, rolling a 2 out of 6 possible outcomes. A single one of those outcomes is a 2. Out of 6 possible outcomes, an even number is 2, 4, or 6. So that's 3 out of 6 of those outcomes, or half of them. So now, if we're looking for the probability, the OR probability, so rolling a 2 or an even number, we have to go and take a look first at whether or not these are mutually exclusive. So is it possible to have both at the same time? So 2 and even at the same time. And this is kind of our key telling factor here. If this is 0, then yeah, they're mutually exclusive. If it's not 0, then they're not mutually exclusive. So let's take a look. Is there any place in our sample space where we have both sides checked off? So a 2 on one side and a 2 on the other side, where it applies to both this probability and this probability. If you see, I kind of made a mark here so we can kind of distinguish where they intersect. And here they actually do have an intersection. On one of the 6 spaces, they do come together. So as a result, we can say that because this is non-zero, they are not mutually exclusive. And secondly, we have to use the other formula, the one on top here in green, to calculate. So probability of A plus the probability of B minus the probability that both happen at the same time. So our final answer for this is 3 out of 6. So the probability that we either roll an even number or we roll a 2. So some key takeaways: it's not mutually exclusive, and we have to use this formula with our additional subtraction problem in it. Let's keep going. We'll do a few more examples here. This time, what if we're talking about the probability that you roll a 2 on a 6-sided die and the probability that you roll an odd number on a 6-sided die? And apologies if there's noises in the background. That is Clover. I promise it's not me. So first off, probability that you roll a 2 out of 6. One of those outcomes is a 2. Probability that you roll an odd number this time is 1, 3, and 5. Idiot, sorry about Clover. So 3 of those 6 outcomes in this case are odd. So the last question here is, what if we have 2 and odd at the same time? Well, let's take a look. There is no intersection. 2 is not an odd number, so it's impossible to roll a 2 that happens to be odd. Just can't happen. So this is a 0 probability. If we look at our chart over here, there's no space where there's an arrow and a check mark. Basically, there's no space where both of these things are true at the same time. So because of this, we can say that they are mutually exclusive. And we use the first formula to find the probability that we get a 2 or an odd number. So we simply actually add them this time. So final answer here is just 4 out of 6, or 2 out of 3. So they are ME, and that's how we calculated it. All right, so a few examples with a die. Now let's go over a few examples with a deck of cards. I'm going to go a little bit faster here because my battery is running low, to be totally honest. I'm sorry if that's giving you anxiety in the top right corner, 5%. We can do this. So probability of a face card and the probability that we take an ace. Well, face cards represent 3 of the 13 types of cards, and an ace is 1 of the 13 types of cards. So what is the probability that we have both a face card and an ace at the same time? And maybe my battery is affecting my ability to write. We'll see. So kind of the key idea here, though, is that you can't have both. Like, an ace is not a face card. So because they are not the same thing, they can't happen at the same time, 0 out of 13 of these types of cards are both face and ace. You're either basically one or the other. So as a result of this, when we are finding the probability of a face card or an ace, we actually can just add up those two probabilities. So 3 over 13 plus 1 over 13, because that last probability is 0. So we're left with an answer of 4 over 13. And in this case, we can say that yes, they are mutually exclusive. If the iPad will let me write. Oh my goodness. All right, so we are going to finish up there, but again, that's the idea going through and calculating these, is that as we are working through the examples, we are trying to see, can they happen at the same time? If the answer is yes, they can, then we have to use our not mutually exclusive example, and if the answer is no, they cannot,